Hey everyone, this is Sean, and I'm here to talk about Svelte and the Great Space Elevator. So this is a talk in 4 parts, and the first part is going to be about how we currently get into space. And trust me, this will be relevant later. So most people will know about Saturn V, which was in service from 1967 to 73, and most importantly, it was the first rocket to get us to the moon. Saturn V had a bunch of stages, primarily like a stage 1 over here, a stage 2, a stage 3, and then finally 90,000 pounds of payload. And of course, when we're talking about Saturn V, which served the Apollo missions, we're talking about payloads that includes these 3 guys. And of course, the total cost of this was about $190 million in 1970 dollars. That's $1 billion in today dollars. And because I said $1 billion, I am contractually obliged to reference Dr. Evil in my slides. And that's how you know it's $1 billion, when there's Dr. Evil on the slide. Okay, but most of you also remember the Space Shuttle program. And fun fact, when we talk about the Space Shuttle, we're actually talking about this whole unit, this whole system over here. It's called a system. And this plane thing over here is actually just a Space Shuttle orbiter, meaning that the rockets, which is the fuel tanks, the liquid fuel tanks, and so the solid rocket boosters, these are also part of the Space Shuttle. So let's look at how much each of these things can hold, and that's a few million in terms of fuel. And pictured here is the space lab where you can conduct experiments. So we went from let's just get people to space and get them back to let's get stuff to space and just do wacky experiments to find out more about zero gravity. So let's talk about the total cost of this. The total cost was $1.6 billion. And because I said billion, I got to reference this guy. And because it's $1.6 billion, I got to reference this guy. And he's so cute. I love him. All right, so I threw in a lot of numbers at you, but one thing I didn't talk about was the scope of reduced ambition in our space programs. We went from flying to the moon and back, which is 384,000 kilometers, to just going to low Earth orbit, which is only 2,000 kilometers. So if you look at the numbers over here, it's not really clear that we've improved over the past 40 years of spaceflight. We're flying less, we're lifting a lot more, and we're spending kind of around-ish the same in terms of fuel and in terms of money. In recent years, SpaceX has really started to lead the next stage of growth. Most of you will remember Falcon Heavy in 2018. This is, again, a rocket designed for a low Earth orbit, but it carries a significantly heavy payload, hence the heavy designation. And because Elon Musk will be Elon Musk, the test payload that was given was his own personal roadster, which of course made for a very memorable image. Look at the cost again. Actually only $90 million, which is an improvement. And primarily the reduced price tag was due to the reusability of these rockets, as well as, of course, SpaceX's excellent engineering overall. But no matter how much engineering you do, you can't really get past what NASA calls the tyranny of the rocket equation. And that is this trade-off of these 3 factors. And basically you can only pick 2. So you want to have lower fuel, or lower costs, right? You don't want to spend so much fuel. You want to ship more payload, which means, that's all the good stuff. That's all the interesting stuff. And then you want more delta V. So delta V is a generalized measure of how much you can change your velocity, accelerate, decelerate, which is basically how much interesting stuff can you do with your rocket. Can you, fly somewhere, change directions, and come back. All that carries a cost with delta Vs. And that would be bad enough, right? Have 3, choose 2. That's a typical impossible trinity type equation. But there's a tricky nuance with this, which is the fuel has to carry itself. So we'll have a rocket, and the fuel cost of the rocket has to be supported by more fuel, and the fuel cost of that fuel has to be supported by more fuel, and so on and so on. That helps us get to deriving the rocket equation, which is a simple relationship between delta V, which is the good stuff, the one that lets us do all the interesting things of our rockets, and the mass ratio, which is a ratio of initial mass over final mass. So initial mass is your rocket plus all the fuel, and the final mass is just the rocket, or your rocket and your payload. So essentially you want that mass ratio to be as low as possible, because that means that you're carrying as much payload per trip as you could possibly be. An ideal payload would be 1, right? You just don't have fuel. But what the Tsiolkovsky rocket equation tells us is that the more delta V we want, the exponentially more mass ratio we're going to need. And that translates basically to exponentially more fuel. That's Konstantin Tsiolkovsky over there. He's not looking too happy, but he came up with it in 1890, way before we even had airplanes. So let's think about the pros and cons of rockets. So the pros, on the plus side, rockets are real. We've flown them for 50 years. We know how to fly them. They also go boom, which is extremely cool. Let's talk about the cons. The cons are that A, they cost a lot of money. B, they cost a lot of fuel, which is not great for the environment. C, they're not scalable because of that exponential slope I showed you. And lastly, they also go boom, sometimes in bad ways. So that's not great. Part 2, how do we make the web? So my primary assertion here is that the web wasn't designed for all the stuff that we make it do. We didn't really predict the proliferation of all these apps when we started designing the original web. Of course, now the web platform has improved a lot, but there's still a lot left that needs to be done, and that's why we all have jobs. And primarily, the web wasn't designed for this, which is the moment we won the web on desktop, the primary computing platform changed to mobile, and now we have a whole new set of engineering challenges, primarily to do with bandwidth, but then also power consumption and raw CPU horsepower. So Alex Russell from the Google Chrome team has done the math. You can look up his blog post to check his math. But basically, he gives us about 130 to 170 kilobytes uncompressed JavaScript for our initial load. And that really should inform how we responsibly structure our JavaScript apps. Of course, on the web as a whole, we've blown past this. I think we're last in range sometime around July 2013. And really, it's going to depend a lot on what framework you start with, because that's really going to give you, the starting point that you can't go lower than. Of course, you can write vanilla JavaScript as well. So here I've obscured, these are from a real Hello World benchmark that I've taken off the web. I've obscured all the names of the frameworks to protect the innocent, if any. But of course, that's just Hello World. If you have something more realistic, there's also the Real World benchmark project, where people take a realistic web app and implement them all in different frameworks, so you can see something that's more than just a trivial Hello World thing. And it seems from this test that the average framework footprint, at least for the popular ones, run up to about 100 to 200 kilobytes. And that's a lot. Just the framework itself, it's going to blow past your budget. So that's something to be aware of. But I also want to impress upon you the fact that it's not just about JS weight. I get it, right? Like, we don't all serve the next billion, and some of us can afford a little bit more JS weight because we're competing with native apps, which have no weight restrictions at all. But here the argument goes beyond JS weight to more developer experience and maintainability, right? Some frameworks just encourage more code, more boilerplate, whatever. And as we all know, the more code you write, the more bugs you write. But then also, just the sheer amount of boilerplate leads you to want libraries to help you resolve all that boilerplate. But then also, that really gives you a lot more decisions to make and a lot more to maintain. And it relies on a lot of open source developers who are completely unpaid to help you maintain that. And that can be very challenging. Like, you can obviously make good decisions and customize your stack to exactly the thing you want, but a lot of times you have a lot of room to shoot yourself in the foot and make really bad decisions and end up shipping apps that are just way bigger than they would have been if you just wrote them yourself. So it's not really clear if this is better or not, but that's just the way things are. Frameworks have just have focused on that core responsibility of being a rendering layer, a really, really good abstraction, and then just focus on being as small as possible while giving you the ability to extend the platform. But it's a little like that analogy of the reduced ambition in terms of the space shuttle. We sent a few dozen people to the moon in the 1970s, and we just haven't been back in the 50 years since. I think the analogy kind of holds when you think about the history of web apps. So if you think about your app as a rocket, we used to start with jQuery as a base, and then we might have maybe jQuery UI, and then we might have some plugins in there, and then we'll have a bit of our code. And that's just, a basic requirement. Send people up to space, get us back to ground. That's about it. But then our requirements change, right? We want to do more stuff on the web. And so we have to bring a bigger ship. Also, our tools evolves, right? So now we have reusable tanks that are all separate pieces and separate components. So here, for example, we have React DOM as like the main fuel tank, and then we have React Router and Redux. And then our code here, we were able to ship more code because we just got a lot better at it. But it's still fundamentally this trade-off, right? Like we still really can't really escape from what you might call the tyranny of runtime frameworks. And essentially, it's these three desirable features. You want all three of them, but you can only have two. So you want more features, you want a higher quality web experience for your users, and you want to write less code, but then you also want to ship less overall JavaScript, including libraries, right? You can only pick two of these, and that's really challenging. Like, let's work through it, right? Like let's say I want to write less code, and I want to have more features. That just means I have to import a bunch of libraries. So the JavaScript weight goes out the window. Or I want to write less code, and I want to ship less JavaScript. That just means I sacrifice some features. So this is kind of a conundrum that we've run into as far as runtime frameworks go, which leads us to part 3 of this talk. So in part 3, we're actually going to go from science to science fiction and try to figure a way out of this conundrum. And essentially, the solution to the rocket equation is inspired by the simplest solution of all, which is just putting down a rope. And of course, it's the same guy that came up with the rocket equation, Konstantin Tsiolkovsky, that came up with the space elevator. And it's essentially is exactly what you think it is. Like, you set up a track, and then you have an elevator that goes up and down, and that's about it. That's all you need to do to get up to space. Of course, that's a little bit wishful thinking, and Arthur C. Clarke wrote a lot about that in the 1970s. But recently, scientists have started actually working on this. And this is a mock-up of how it looks. We're likely going to have multiple stations because there are multiple points of interest for people to get off. So it's not just about the geostationary orbit station at 36,000 kilometers. You also need to stretch out all the way with 60,000 more kilometers to the counterweight, because essentially you're swinging this rope around Earth at the speed of Earth's rotation, which is quite a lot of speed, and you need to have a counterweight to balance it out. Essentially, though, the system's going to really consist of 3 parts. First is the base. Most artists' impression envision it in the sea somewhere because it's just pretty. And then there's the climber. This is the actual module that you'll get in, and it climbs up. The trip will probably take about 3 days, and it's an open question of how to power this thing. If you strap rockets to it, then you're not really any better off. And so the main leading solution right now is to actually beam laser power to it, or actually propel it with lasers itself. And then finally, there's the stations, and obviously there can be multiple stations. And so in terms of raw physics, this theory is actually pretty validated, because with rockets, you're not just going up, you're also having to turn. And this is a pretty familiar term for those of you who play Kerbal Space Program, which is after you're up, after you're sufficiently high enough that air resistance isn't so much of an issue, you start turning so that you can actually orbit Earth rather than just go vertically straight out. When you're in a space elevator, however, the station up there is already at geosynchronous orbit. So all you have to do is go from Earth to the station, and then you're already in geosynchronous orbit. So there's no additional delta V needed to make the turn. And obviously everything's guesses right now, but if you put this on a cost curve, here's where we are in terms of where we think cost per launch is. And the space elevator is all the way out there. We're probably about 40, 50 years away. And this is completely hypothetical, right? We may actually hit some sort of asymptote much higher up, and we may not be able to get past that with rockets alone. But as far as we know, the best information that we have right now, it costs about $20,000 to send a kilogram up into space. And our best guess is that space elevators are only going to cost $200 to send a kilogram up to space. To give you these numbers in something more relatable, it's going to cost about $1.3 million to send the average human up to space with rockets. And with space elevators, it's going to cost about $7,000. So that's the same order of magnitude as the cost of a flight. And that's where we start to get really interesting options in terms of what we can do out in space. I also want to impress upon you that it's not just about tourism. It's also about becoming a spacefaring civilization, because the needs of spacecraft going from surface to orbit is very different from going planet to planet. So ideally, we want to build a spacefaring equipment in space so they don't have to deal with atmosphere and gravity, and they can just focus on the single problem of traveling through massive distances in space. But anyway, back to the economics. The investment profile of these two solutions are also very different. With rockets, there's some upfront investment. Basically, you need a launch platform and some R&D. And then per trip, you have to rebuild the rocket each time. It only gets a little bit better with reuse because even the Falcon 9 rockets, you can only reuse them about 10 times. So with the elevator, obviously there's a huge unknown upfront investment, but the promise of it is that per trip, the cost will be minuscule. So of course, with any investment profile that looks like this, there's probably a crossover point where it's actually more interesting for us as a species to start investing in elevators rather than rockets. And it looks like the crossover point is about 2 million tons, which is 2 space stations. Very, very achievable, except for 2 problems. And the first one is space debris. So unfortunately, ever since we've gone up to space, we've left junk in space, and it's just grown exponentially ever since we've been up there. The pictures that we see of space are not as clean as artists envision it. This is the actual reality, where it's just covered in a bunch of junk that we've just left up there. So any space elevator solution is going to be buffeted by all this space junk. So either we clean it up or we just invent something that's super, super strong and resilient. Problem 2 is the tether material. This is probably the most well-known downside of the space elevator. Right now, the best solution that we have is carbon nanotubes, so we don't know how to manufacture those in massive quantities that we need. Remember, we need about 96,000 kilometers of this thing. It's probably not going to be glass, which would be really cool, but it's just not happening. But one compromise could actually be to build it on the moon. And so you can kind of think about this as an MVP, because essentially a lunar elevator is going to have all the same requirements, but none of the difficulties that we have. Like we don't need as much strength because the gravity of the moon is not so big, and there's no space debris, so that's great. And so we can actually test out this idea and just make it more economical for us to get down to the moon, where we can start mining for materials and we can start building in space. So that seems like the more reasonable first step. So all of this speculation with elevators brings us to part 4, compilers as the future. The goal of this section is to take everything that we've learned so far and apply it to JavaScript and the future of web development. So this section was inspired by Tom Dale, who wrote a blog post in 2017 saying compilers are the new frameworks. And essentially his conclusion is exactly what I've been talking to you about all this while. He says frameworks are transforming from runtime libraries into optimizing compilers. And when it comes to eking performance out of runtime libraries, we've basically reached the point of diminishing returns. And if you survey popular frameworks today, you can see that they're all working on some form of this. Like Vue 3 is rewriting its APIs to be tree shakeable. Tom Dale, of course, is on the Ember team, and they've had Glimmer since 2017. React, maybe you could count selective hydration, Gatsby, or Next.js in this category. And Angular is seeing a very dramatic improvement when it becomes an optimizing compiler. So let's actually have a look at what Angular is seeing. So the results of Angular is basically seeing about a 90% decrease in terms of its output, because it's just not bundling things that you don't use. And this is actually seeing more impact in terms of large apps, which of course need it the most. And so these are all very, very positive improvements for the future of the web, especially the mobile web. But of course, we're not here to talk about Angular. We're here to talk about Svelte. So if you go onto svelte.dev, the main site, you can actually see that the main pitch is 3 pillars. A, you write less code. B, there's no virtual DOM. And C, it's truly reactive. So we'll go through each of these in turn, and I'll add some perspective of my own. So the first point is about writing less code. Here I'm actually drawing from a blog post that I wrote comparing Svelte and React, because that's basically all I know. And in React, forms are known to be hard. There's a lot of boilerplate involved in setting up and managing the state for each element in the form. Whereas in Svelte, it's idiomatic to use two-way binding and handy helpers that have been built into the language itself. And so this is a trade-off. It's not free. Like React intentionally chooses this so that they don't make you learn extra syntax. Whereas Svelte says, we'll make you learn extra syntax, but it will make sure that it's worth it for you to use it, because it's just a common use case. So it's really up to you which one you want, but that's the value proposition of Svelte. And based on my own experience, which is not a professional benchmark, it's just personal anecdata, I've rewritten a couple apps from React to Svelte recently, and I can attest that it's about 20% less code. In terms of the final JavaScript bundle, I actually ported my own personal site over from Gatsby to Svelte, and I saw about 93% less JavaScript in the final output, while preserving features like client-side routing, dynamic theming, and search. I should stress again that these are not real benchmarks, but these are just me rewriting apps from React to Svelte just to see how it feels. Now the second point is that there's no virtual DOM, and in order to get this across, I'm going to have to take you into actual code. In order to explain what no virtual DOM means to people who have only been using virtual DOM, I have to reintroduce the DOM. So here we're using the most simple demo I can think of. We just have raw HTML with a head element and a body element. I'm going to head to the console and write the minimal JavaScript that's needed to dynamically render something on screen. So I'm going to create an h1 element, assign it the content of hello world, and append it to the body. That's how you would write this by hand. Now let's try for something more interactive. I'm going to refresh and paste in my pre-prepared code. And here I've created an input box with a callback that updates a global variable called world, and that updates the h1 element dynamically. So here I can actually show that I have some interactive element, and there's no concept of virtual DOM. It's directly manipulating the DOM element. So it's with this context that we can start to evaluate Svelte. Svelte's a compiler framework, so what you write isn't actually what you ship as JavaScript. So here we've written a basic Svelte template, which is essentially a script section and then an HTML section with some template syntax. So if we go through the compiled Svelte output, we can see that there's a C lifecycle, standing for create, that calls an element function that comes from the Svelte runtime. And if we look up the source code of the Svelte runtime, we can see that it's just a simple alias for document.createElement. So that's pretty intuitive. And then obviously it sets text content just the same way that we did. Now let's go over to the render result and write some interactive inputs, just like we did before. I'm simply going to declare an input, and I'm going to bind to the value attribute of the input, and I'm going to assign it to name. And now when I close that tag, a name input is generated, and I can interact with it like I have before. Let's look at the generated JS output and see how intuitive this is. So here in the C lifecycle, standing for create, I have a bunch of elements created. In the M lifecycle, I have a bunch of elements mounting. And then in the P lifecycle, I have a bunch of elements updating. So here, for example, it's calling set data and set input value from the Svelte runtime. And if I can look them up again in the Svelte code base, set. These are all just simple aliases for DOM APIs, text.data, and input.value. What I'm really trying to get at is that there really is no virtual DOM. Svelte literally compiles your template code down to the direct DOM instructions that you would otherwise have to handwrite yourself with vanilla JavaScript. So it's as close to writing vanilla JavaScript as you can without tearing your hair out, and therefore has performance approaching vanilla JavaScript. There are other features of Svelte that I don't have time to explain, but something that React developers should definitely be aware of is that styling is included, and it's real CSS, and it's scoped to the component by default. This feature just makes me smile whenever I use it. If you want to learn more about the compilation process, start with Tan Li Hao's Compile Svelte in Your Head blog post. And this is an excellent guide, step by step, as to what Svelte does under the hood, so all the compiler magic goes away. It's shockingly understandable. Let's talk about that last official selling point of Svelte. It's truly reactive. What does that mean? So here's the maintainer of RxJS, Ben Lesh, expressing excitement that RxJS just works with Svelte because it implements the observable interface. Inside of Svelte, there's a handy $ syntax for setting and getting values from stores. For more information, you can check out the Intro to Svelte stores I did at the Svelte Society New York City meetup, back when we used to have meetups. Before we leave this topic altogether, I feel the need to show you one final feature of Svelte stores. Because Svelte stores are just an interface, anything that implements a store interface is automatically a store, and therefore is interchangeable with any other store. This is really helpful. So here, for example, I have a writable store, and this sets a value from 0 to 100, and this is a progress bar, for example. Now, if I set this up and I'm happy with this value, and let's just say I want to animate it. In a typical framework, I might have to swap out the implementations to something heavier to do the animation. So what I can do here is import tweened from svelte/motion instead of svelte/store, and I can make my progress variable a tweened store. So now when I set values, the tween store knows how to call back every single animation frame with intermediate values without me telling it to. And that really decreases the bar for improving user experiences, from doing a basic working product to polishing it with animations and transitions. Svelte is full of awesome surprises like this. And in fact, that's one of the undersold selling points that I personally really enjoy. So instead of all this decision fatigue, you have a bunch of really good first-party APIs. Of course, it's only included in your final output if you really need it. This is literally only possible if your framework is a compiler. There's so much more to Svelte that I really enjoy. There's really great docs. There's simple internals that you yourself could understand, like I've already shown you. There's less emotional baggage. There's a really friendly community. And finally, this may be a little bit hard to understand at first. I'm going to start from a completely empty folder. Then I'm going to install Svelte and Svelte. And finally, I'm going to add a base index.html. Now I'm going to paste in a pre-prepared Svelte component, and then I'm going to make sure I have a package.json. Now I can run Svelte. Watch closely, there's no editing right now. That's the build, and now I have my running app. Because Svelte uses Snowpack, there is very minimal build time because there's no bundler involved. And that's the kind of tooling that you can come to expect when you deal with anything in the Svelte ecosystem. Everyone is very focused on developer experience and focused on betting on the future. And just to sum up this entire talk, here's the pitch in 2 slides. A runtime framework involves libraries, more libraries, and then finally your app. It's basically recreating the rocket from scratch every single time. With a compiler framework approach, a core team is responsible for maintaining all the batteries that you need to get from 0 to hero, including server-side rendering, and all you do is write your app logic, and that's very appealing. And you can have this now instead of 50 years from now. Runtime frameworks have a small core team, and that necessitates a large community of open source developers to patch every other thing that you typically use to write apps. A compiler framework will probably have a larger core team, even though Svelte is relatively small right now. But that means each individual developer can do a lot more on their own, and you can write apps with a lot less code, and therefore write a lot more features and a lot more apps. So that's all I wanted to share with you today. If you wanted to get started with Svelte, definitely check out the 30-minute tutorial at svelte.dev/tutorial. Join the community, and join the Discord community. Check out Rich Harris's talk on rethinking reactivity. And also, if you want to check out a full day of Svelte events, we're holding a Svelte Society Day on April 26th. Obviously, it's an online meetup, and you're welcome to join for free. If there's any questions, you can contact me on my site, or I'll take them now. Thank you.